Hello everyone. I think we shall start now. So, am I audible?
Yes, ma'am.
Okay. So, let me present my screen.
Yes, ma'am.
Screen is visible, right?
Yes, ma'am.
So,
Yes,
good,
ma'am.
yeah. Good evening, everyone. This is Chinmay, PMRF scholar from IIT Madras, and we will be taking the live interaction session of advanced machining process. Okay. So today's assignment will be on electrodischarge machining process actually. Okay. So I'll like briefly explain about that electrodischarge machining and its working principle. Then we'll move into some numericals and some questions answer. Okay. So first, like from the figure itself, we can see what are the parts of that electrodischarge machining process or machining. So in that actually electrodischarge machining is a non-traditional process, that is electrothermal based non-traditional process, and of which like in which electrical energy actually is used to generate electrical spark, and that material removal actually mainly occurs due to that thermal energy of the spark. Okay, so in EDM, actually a potential difference is applied between the tool and the workpiece. We can see that workpiece fill and the tool. So here a potential difference actually is applied, and then like both tool and workpiece should be a good conductor of electricity. Okay, so we'll go to that in later. The tool and workpiece work materials actually immersed in dielectric medium. So what about dielectric medium? I'll discuss it later. So that like actually generally that kerosene, deionized water, those are used as actually dielectric medium. So both tool and workpiece material will be immersed in that dielectric medium. So actually gap is maintained between the tool and that workpiece. So depending upon that potential difference only, and that gap which is generated between that, which is there between that workpiece and the tool, that actually their electric field will be generated. Okay, that tool actually is connected to the negative terminal of the generator. We will be seeing the how the generator is working to flow the electricity. We'll come to that RC circuit and all those generators. So here basically what happens, that the tool actually is connected to that negative terminal of the generator, and workpiece is basically connected to that positive terminal. Okay, so that electric field is established there between the tool and that workpiece material. Okay, so the free electrons are there on the tool. Those will those will produce that electrostatic force actually. So if that like function on that bonding energy of that electrons produced is less, then electrons would be emitted from that tool. Okay, so that's like emission of electron. We can also say this as like cold emission, we can say it as. Okay, that so that emission of that electron, or say cold emitted electrons, then will be accelerated towards the job is, say we can say that green color workpiece. Towards that workpiece it will be that, just a minute. Okay, so that electrons, actually what we are talking about, that electrons that those electrons will be accelerated towards that job through that dielectric medium. That dielectric medium you can see in the figures. Okay, those can be kerosene or say deionized water, okay, or say some solution of any which base solutions. So that, like, mm, those electrons, after that, like emission of those electrons, the velocity actually gains and that energy produces, and that start actually moving towards the job. Okay, so there would be some collisions between that electrons and that dielectric molecules present in the dielectric fluid. Okay, such collision may result actually in ionization of those electrons and dielectric molecules and that energy of that electron. Okay, so these electrons actually are accelerated. So in this way, actually, that generate like electrons would get generated due to that collisions itself. So this cyclic process actually, basically what it does, it increases the concentration of that electrons and ions in that dielectric medium region. So, and that, like in between the tool and job, like tool and that workpiece, a spark gap is generated. Okay, so sorry, that electrical, that resistance of that such spark or say plasma channel, like will be very less, we can say. So there, or like suddenly that large number of electrons like actually flows from the tools to that workpiece. Okay, so that's that electrical resistance of this plasma actually is less. So all of a sudden, what it does, like large number of electrons actually flows from the tool to job, and ions from the like job to tool. Okay, so that such movements of from job to tool and like workpiece to tool and tool to workpiece, due to that, like movement of that electrons and ions actually seen as a spark, like it generates as a spark. So that electrical energy actually is dissipated like in the form of thermal energy of that spark, and that thermal energy of that spark actually removes the material from the workpiece surface. Thus, in this manner itself, like that electrodischarge machining process works. So that high speed of electrons actually impinge on the workpiece and ions on the tool. Then the kinetic energy of that electrons and ions with the surface of that like workpiece and tool will be converted into that thermal energy, or say we can say heat flux itself. So in this way, like we can say, even you can see some questions like that heat flux leads to that extreme rise in temperature in that region. So what will be the range of the temperature rise in that region? So you may like see like the temperature will be in around 10,000 degrees Celsius. That much temperature actually it's there in that much temperature rise in that region due to that heat flux. Okay, so we have like the first question here is that which of the following statement is not true? Like material removal mainly occurs due to the thermal evaporation and melting. Dielectric fluids should provide an oxygen free machining environment. And number C is work material to be machined by EDM has to be electrically non-conductive. As we have seen, like we have that material, workpiece material has to be like highly electrical conductive material. So that option C is not true, because here it's there that work material to be machined by EDM has to be electrically non-conductive. No, it should be that electrically conductive materials. Okay, and like that the workpiece actually made positive and the tool is negative, so that electrons actually strike the workpiece to form actually crater, in form of crater due to that high temperature and melting. That's in this manner actually material removal starts, and that like a constant voltage is not actually applied here. So only sparking is desired in that EDM, like rather than arcing, we can say. Actually arcing leads to that localized material removal at particular point. So here actually sparking is desirable. Okay, so moving to the next, actually this is the waveform which is generated in electrodischarge machining process. So that waveform, like process parameters of that waveform, actually is some parameters are there, basically in which that spark and all those things works in EDM process. So I'll be mentioning, like, one is, it's not working. Okay. One is open circuit voltage. This is VO. Then another one is working voltage. Just a minute. So, my voice is not clear. Actually, someone is telling that voice is
Clear, mom.
okay. Okay, fine. So, working voltage is VW. Those are the process parameter. Actually, I'm mentioning the maximum current. So, maximum current will be IO, or that pulse on time and pulse of time we'll see later. Like pulse on time, actually basically that duration for which the voltage pulse is applied, so we can denote is as a T on, and pulse of time as T off. Then spark gap, we have already seen that what is spark gap, that is delta, that is gap between that workpiece and tool. Okay, then the like dielectric medium is another important process parameter, dielectric medium. Then that polarity, like
I'm right most clearly.
okay, you are not understanding. Okay, sorry, actually I'll try. Actually notepad, it's not clear. Okay, so first one is open circuit voltage. I am again repeating, first one is open circuit voltage, that is VO. Second one is that working voltage, that is VW. And third one is maximum current, IO. When we'll be solving or deriving the equations in later like slides, we'll see like what are the parameters actually using in that diagrams. So one is maximum current, that is IO. That is one is pulse on time, that is pulse on time. We can say that duration for which that voltage is applied, actually that T on, that pulse of time is T off. And spark gap delta, that is the gap between the tool and the workpiece. Dielectric medium is there and polarity is there, that tool is connected to the positive and workpiece is connected to the negative, we have seen, right? So here two questions are given is, which of the following cannot be used at dielectric fluid? So basically dielectric, if we say about dielectric fluid, like in EDM, like material removal mainly occurs due to that thermal evaporation of and that melting. So that thermal processing is like required to be carried out in absence of oxygen, actually, so that the process can be controlled and oxidation can be avoided. Actually, we want to avoid here oxidation. That's why in absence of oxygen itself, that thermal processing is working. Okay, so that oxidation of like leads to that poor surface even conductivity. Okay, of that workpiece. So that's why dielectric fluid, we have seen that dielectric fluid should provide an oxygen free machining environment. Okay, so here there is huge importance of that dielectric fluid itself. So that, like, generally kerosene deionized water we have seen is used as dielectric fluid in EDM, but tap water we can't use actually, because like it ionizes too early and break down due to that presence of salts in that tap water, so it's breakdown. Okay, so that impurities occur there, so that's why electric tap water cannot be used as a dielectric medium here. Okay, so actually what it does, dielectric medium actually flushes around the spark zone. So that's the reason actually the tap water can't be used in dielectric as a dielectric medium in EDM process. So the right answer would be tap water. Okay. And tools shouldn't have obviously that low thermal conductivity, high machinability, high melting point, high specific point. High machinability should not have that, high melting point should not have high specific impact. Tool should not have low thermal conductivity. It should have high thermal conductivity. So the right answer will be the option A. Now we'll come to that uh, like RC type circuit generator, which I have told in the first slide itself. We'll come to later, like come later to that topic, that generator, RC type generator, that is resistor capacitor type generator. Basically what it does, like resistor and capacitor, we know that we have studied in our other courses that what resistor does, it dissipates electrical charge, and what capacitor does, it actually stores electrical charge. Okay, so that both like are passive components, we can say, in electrical circuit. Okay, resistor and capacitor. So both resistor capacitor circuit actually it's consists of both like resistor and capacitor, and it's actually driven by voltage source or current source. Okay, so how it works in EDM process we'll see like now, like, so that in RC type generator, actually the capacitor is charged from a DC source. Okay, so that like once that breakdown voltage actually is reached, that capacitor would start discharging. Actually, in that process, two phases are there actually. One is charging phase and one is discharging phase. Okay, so that spark actually will be established between the tool and workpiece, and then discharging will continue as long the spark can be sustained. Okay, so just a minute. Okay, so like this discharging actually will be continuing up to when like the spark can be sustained. Okay, so that like voltage becomes like too low to sustain the spark. Okay, that we can see in the derivation itself. So just a minute. We can derive the expression in such a in two phase. Actually, one is charging phase and one is discharging phase. What happens in this charging phase is like capacitor is getting charged. Okay, but how? It's getting charged at any instant of time in VC. See, in that diagram, V0, VO, you can say that is open circuit voltage. Okay, so actually at any instant of time, that is VC. VC is varying current, like varying voltage, and that like it's getting that charged at any instant of varying voltage VC. Okay, then that charging current will come into our picture, that is IC. Okay, so that IC or like IO, that is maximum current, will be achieving when at condition at t equals to 0, at time equals to 0, that will be maximum, that will be IO. Okay, so we'll see like that like that IC also we can derive as dV by dt. Okay, just a minute. Okay, so dv by dt will be vo minus vc by rr will be the resistance. Okay, so if we if we expand this equation as dv by v0 minus vc or vo minus vc, open circuit voltage minus varying voltage, will be 1 by CRC into dt. Okay, so like IO, when we can get that IO at condition, if we starting condition, if we write it as, if we write it as at t equals to 0, Vc equals to 0 and t equals to Tc, Vc equals to Vc star, that is varying voltage, then if we integrate with respect to some values like some limits, that is 0 to Vc star, if we integrate this, then dVc by V0 Vo minus Vc equals to 1 by CRC 0 to Tc dt. Okay, and if you integrate, what you will get? If this expression you will integrate that from 0 to Vc, if you integrate that voltage, and 0 to Tc, if you integrate the T dt, then what you will get? From this expression you will get, if you simplify and integrate this, you will get Vc equals to, Vc equals to Vo into 1 minus e to the power t by Rc into C. Okay, if you integrate this equation, then you will get Vc equals to Vo into 1 minus e to the power t by Rc into C. We know that notations, what like Ic will be the charging current, V will be the open circuit voltage, Rc is the resistance, charging resistance, C is the capacitance, and Vc will be the like capacitor voltage during the charging. Okay, so we from these, like we can derive that what will be the IC, that is charging current. Our main motive is to like calculate IC. Okay, so what will be the then charging current or IC? We know that IC is V0, that is dV by dt, that is charging current only. Okay, so that is V0 Vo minus Vc divided by Rc. So if we put the values of Vc from here, like Vc, we have found out that Vc equals to V0 Vo into 1 minus e to the power t by Rc into C. So if we put this value in place of Vc, then we'll get Vo minus Vo into 1 minus e to the power t by Rc into C. Okay, divided by Rc, right? So then if we simplify it, we'll get Vo into 1 by t to the power t by Rc into C by Rc, or if we more simplify more, then Io into e to the power t by Rc into C. Those formulas actually will be important for those solving the numericals in later stage, we'll see. So that actually during the charging, what happens, like that electrical load actually coming from the TDM, so it may be assumed that like totally resistive. Okay, and is characterized by machine resistance, which is denoted by Rm actually. So then like discharging current can be like calculated or derived in terms of that equation as ID, which is denoted by discharging current. See, in discharging phase, this capacitor is there is at initial value of Vc. Okay, that capacitor that voltage we have seen, like Vc, that instantaneous capacitor voltage during the charging, that will be in initial value, that will be the initial value during discharging phase. Okay, so that discharging phase, that capacitor is will be at initial value of that Vc at discharging current at Id, that is okay. RC type means what exact? Actually, this is a kind of resistor capacitor. We have seen in electrical signals also that RC type circuits, which is that resistor capacitor circuit. What it does actually, it basically consists of resistance, a resistor or and capacitor both. So what it does, like in resistor, it dissipates that electrical energy. In the meantime, the capacitor, which actually stores the electrical charge. Okay, so both is a both with consisting both resistor and capacitor. Actually, it's driven by that by applying that voltage source or current source. Okay, so this kind of circuit actually works in generator as generator to flow the current in EDM machine. Okay, so here ID will be that. Okay, what will be there? Okay, we have to find out that discharging current now. Okay, we have seen the derivation of charging current. Now it's like time to solve the discharging current. Okay, so these will be like voltage by resistance will be current, right? Machining resistance, or we can denote it as a also in terms of minus C into dVc by dt. Okay, so that IC, okay, minus C into dVc by dt. Okay, IC like Vc, we have seen that capacitor voltage like during the discharging, that and that Rm will be the machining resistance. Okay, so IT will be denoting as Vc by Rm, that is voltage by resistance, and from that, like if C is the capacitance, now we can denote it as a minus C into dV by dt. Okay, so actually why this minus is coming in that equation? This negative sign actually represents that Vc or that capacitor voltage actually gradually decrease during the discharging phase. Okay. So now if we give some condition like at t equals to at t equals to 0, if we give some condition, that is like start of discharging or that initiation of spark, we can say Vc will be Vc star and t will be Td, discharging time, and then Vc will be that Vd. So if we'll Vd star, we can say if we integrate into some limits, that is Vc to Vd. Here why Vc is the initial, because we have told, right, that in discharging phase that capacitor is at initial value of Vc star. So the lower limit will be Vc star only and upper limit will be Vd. Okay, and if we integrate that voltage dVc by Vc equals to minus 1 by Crm into 0 to discharging time. Okay, with respect to time, if we integrate it and if we simplify it, we'll get Vd. From Vd we'll get here like Vc star by Rm into e to the power Td by Rm into C. Okay. So that discharging of machining current ID we have to find. Okay. Discharging current, that is Vd by Rm. Okay. That is Vd we have like calculated, right? Okay. So we have found out two expression. One is discharging current and one is charging current. Okay. So one is Vc by Rm into e to the power minus t by Rm into C, and one will be that V0 minus Vo minus Vo into 1 by 1 minus e to the power TRC. If we simplify it, we will get Io into e to the power t by Rc into C. Okay. So we have seen two expressions. And actually, why we are finding out discharging and charging current? Actually, we have to find out T on or T off time. What we have seen in the notations, okay? Pulse on time and pulse off time. So in like just a minute. So from this figure itself, that right side figure itself, it can denote. See, P I see one is voltage, one is charging current, and one is discharging current. From this diagram itself, actually we can say. Okay. So in first phase, what it happens, like with T off, it's like during charging that V voltage actually increases. We can say that figure itself, the diagram, it's actually increasing. Okay. Okay, so with during charging that V increases, that voltage increases. So that is TC, that charging time, it will be equivalent to T of time. Okay, T of that pulse of time, and and it gradually then decreases. We can see. So this is T on, or like TD, discharging. In that discharging phase, actually it's decreases. So it will be equivalent to pulse on time. Okay. Similarly, if we come down into that IC by T phase, so here it will like see like that, on time, during that on time, charging current is not there. You can see that, like here, no charging current. Okay. So if we come down to that ID by T phase, we'll see like here, like that machining current is there. Okay. This is on during that discharging phase. During discharging phase, we can see this is on. Okay. So that machining current will be on during that discharging phase. This is T on. So if we like come to that cycle time and frequency, actually it's important to find out that TC and TD. So it actually, that cycle time and frequency operations, it happens when like one condition is there, that Vc will be, that Vc star will be 0.716 of Vo. Okay. that occurs at maximum power output. Maximum power output. Okay. So in this way, like if we calculate that we have, if we can derive the expression of actually Tc and Td. Tc will be C into C log of 1 minus Vc star by Vc, and Tt will be minus Rm into C ln or log of Vt into C. Okay, and frequency is derived by 1 by charging time plus discharging time. Okay, if you put it into the equation, you can find the frequency. And one more important derivation or important formula you have to remember, that spark energy. You may have to solve the numericals using that equation, that is, you can write it here. Okay, so spark energy, if we denote it, is ES. If we denote it is ES, it will be integration of 0 to discharging time, and ID, that is discharging current, into sorry, like where they are there. Okay, so it will be that ID square into Rm dt. With respect to t, if you integrate that, you will get spark energy. Okay, so we'll get, if we simplify this, you will get half CVC square. Okay, so you remember this equation ES equals to, later we'll solve one numerical using this equation only. Spark energy equals to half of CVC square. Okay, capacitance into voltage, instantaneous capacitor voltage of square is spark energy. Okay, so just a minute. So here, like how from the picture tells that how the crater actually forms in while like material removal process. So how that removal of material takes place, actually based on one model itself, that material removal is process is like explained. So here, like we have to remember some material removal equations as expressed as, we can say, this is material removal rate is 2 by 3 of pi r, sorry, pi r cube. Okay, so that r is the radius like which forms due to single pulse or spark. Okay, so if ES, that spark actually is given as VI, voltage into current into t on time or pulse time, pulse on time, and like if we that it, like it can be assumed actually material removal in that sparks, single spark actually would be the proportional to delta S into delta S, sorry, is proportional to spark energy. Okay, if you calculate finally a material removal rate, it will be denoted as G into VI T on divided by T on plus T off. Okay, that is G into Vi 1 plus T off by T on, that is pulse of time by pulse on time. Okay. G actually comes from that delta S equals to, if we like put it in as a G is a constant of G into ES. Okay. So per cycle, if we can then calculate. So here one question is there: surface finish can be improved by decreasing working voltage, increasing working current, increasing pulse on time. So from the question, like from the equation of material removal rate, we can say like by decreasing working voltage itself, surface finishing can be improved, because that MRR is directly proportional to working voltage. Okay, so if working voltage is increased, that MRR will be increased, so that surface finish can be improved. Then that's like surface finish will not that much good, so surface finish only can improve when the working voltage will be decreased. Okay, so the correct answer is option A. Okay, now we'll solve one numerical. During calculation of MRR in ATM, supply voltage was used as 55 volt in place of the actual supply voltage of 45 volt. What is the ratio of the actual and calculated MRR? Assume that the condition for maximum power delivery to discharging circuit is satisfied. So,
Cable is there. So
okay. So the question is given as during calculation of MRR in ATM, supply voltage was used as 55 volt. Okay, so we have seen MRR is directly proportional to energy by spark plug or energy per spark. Okay, so energy that we have seen the equation, right? ES equals to half CV square. Okay, that C is the capacitance and VD is the discharge voltage, or say, so that MRR we can say is proportional to E proportional to VD square. Okay, so this relation, using this relation we can write it in such a way that that voltage actually is given as supply voltage VD, that is for one is given as VD1 is given as 55 volt, and one voltage is given as VD2 is 45 volt. Okay, or that like that voltage actually was used for calculation, that is 55 volt, and that actual voltage is given as 45 volt. Okay, so if we write it in that way, like MRR actual divided by MRR calculated equals to V square actual divided by V square calculated. Okay, so V actual is given as 45, so 45 square divided by V that was used actually calculated was as 55, right? 55 square. So what will be the value of that? What will be the correct answer? So anyone has calculated it? So have you calculated this value? Here. It's simple, right? Actually, one you can relate the equations as MRR is directly proportional to that energy per spark, or we have seen that derivation, right? ES equals to half CV squared. So if we write it in such a way, MRR is directly proportional to E, that is like it's proportional to voltage itself, voltage square. So if MRR actual by, if we write it in that ratio manner, we can write MRR actual by MRR calculated equals to V square actual by V square calculated. So V square actual is given as 45, 45 square divided by 55 square. What is the value? Right answer. Point 0.40 is coming. Actually, I have calculated it's coming near to 0.67. Others, have you calculated? Anyway, if we calculate 45 square divided by 55 square, we'll get 0.67, right? Is it correct? Yeah. Okay, that moving to the next numerical. So it's very simple. Like in a RC type generator, the maximum charging voltage is 80 volt and the charging capacitor is 100 microfarad. Determine the spark energy. So spark energy equation we have seen. Yes, because that's why I have told that this equation is very important to solve the numericals. Half CV square. Okay. So here one thing we have to remember that all the units we need to put it in same like manner, that is in SI unit if you put. So that capacitance is given as microfarad. So here half into, if we convert it into the Faraday, so 100 into 10 to the power minus 6. Okay, and P is given as 80 volt. Okay, what will be the correct answer? Like, say what will be the answer for this? Half into, okay, 80 square. Half into 100 into 10 to the power minus 6 into 80 square. So what will be the answer for this? 100 into 10 to the power minus 6 into 80 square divided by 2. So what will be the answer for this? Spark energy? Have anyone solved? Okay, it's 0.32, I guess. Okay. So
0.00.
what?
0.0032, ma'am.
Okay. Okay, anyway, I'm getting 0.32, so you can check the answer, okay?
Okay,
So,
ma'am.
yeah. Okay. So, moving to the next question is, if in RC type generator to get an ideal time of 500 microsecond power. That's for open circuit voltage of 100 volt and maximum charging voltage of 70 volt. Determine charging resistance, and they have told to assume C as 100 microfarad. Okay, so what are given in this question? So TC is given, right? Charging time is given as 500 microsecond, or we can say 500 into 10 to the power minus 6. And what are the other things are given? VC, the charging voltage is also given, right? VC star is given as 70 volt. Open circuit voltage, that is also given as 100 volt. And what are the other things are given? C is given 100 microfarad. Sorry, 100 microfarad, 100 into 10 to the power minus 6. That's all right. So we have seen in the derivation itself TC equals to minus RC into C, L to 1 minus VC star divided by V. So if we put it into this equation, TC is already given. I will put it into minus 10 to the power 6. What we have to determine the charging resistance. Okay, that means R we have to calculate. Okay, into C is given as 100 into 10 to the power minus 6 divided by log of 1 minus 70 is given 100. Okay, so if we calculate this, what will be the value of RC? 1 log of 1 minus 70 by 100. Okay, is coming as minus 1.2. Okay, minus 1.2, that means 500 into 10 to the power minus 6 into minus 1.2 equals to minus RC into 100 into 10 to the power 6. If we cross this 10 to the power minus 6 and 10 to the power minus 6, so RC will be getting as RC equals to what will be like 500 divided by 100 into 1.2. If I'm not wrong, that 5 into 1.2, 5 into 1.2, it's around 6, right? 6 ohm, 6 ohm. Are you getting like this? Is it okay?
Yes, ma'am.
Okay, okay, fine. So those are the few numericals I tried to show so that you can get an idea to solve your assignments. So those are the formulas like which we have to use to solve the numericals, and the basic parts like how the TDM machine is what is the importance of dielectric medium, how that what are the process parameters to affect that processing. Those things we need to actually look into that. Okay, so that's all for today. So apart from this, anyone having any doubt? Yeah, sure. So I have shared my mail ID. You can reach to me if you have any technical problems like this. So shall we close the meeting?
Thank you, ma'am.